Okay, so we're looking at the spring mass model, and the idea behind that, is that we're going to learn why ay double prime plus by prime plus cy equals 0, or equals f of t, is sometimes called an oscillator model, or a model of oscillations. And so the spring mass model is a good kind of template model for us to work with. Just a couple of things to remember kind of outside of this class. We've talked about this before. G is going to be the constant of acceleration on Earth for gravity. Okay, it's either 9.8 meters per second squared or 32 feet per second squared, and it's not exactly that, but those are good enough approximations. Okay, and also Newton's second law is the other thing we're going to need to remember. Newton's second law is that force is equal to mass times acceleration. Now for us, in terms of a differential equation, right, we use this when we were formulating the model of a falling body. And so acceleration is the derivative of velocity. Or second derivative of displacement. Okay, displacement meaning you can have plus or minus, right? It's not really a distance traveled. It's a like signed position, if you will. Okay, so I think with those two things, we're able to work through some of the ideas here. And so I'm going to build my mass spring model, or spring mass model, on a ceiling with a spring that hangs down. Okay, and so this length, the natural length of this spring, is going to be what we denote by script L. Okay, so that's the natural length of the spring. Nothing's happening. And then what do I do with the natural length? I attach a weight to it, which stretches the spring out, presumably. Okay, and then the weight is at rest. Okay, and then the length from natural length to the new length here is going to be our length L, capital L. So capital L is the length that the spring has stretched when we attach the weight. Good. And finally, I've got one more piece of notation that I want to bring in here, and that is my weight is going to be in motion, and so I need to define the displacement from rest. So I'm going to go ahead and maybe make this red right here. This is our kind of distance at rest here, right? And so the distance from here to here is now going to be our u of t, where that's displacement. And just in keeping with our book's notation, down is positive. And so if the spring had been compressed for let's see, maybe I can fit a little picture in here. If the spring had been compressed, if it's going up, right, that would mean that this is negative value for u. Okay, and so stretching is positive, compressing is negative. Good. All right, so that's our notation. U of t is going to be our displacement, and we want to model u of t. Good. All right, let's see if I can keep my picture up here. Well, I want to investigate four forces, I think. Four forces. Remember, when you're building a model, you want it as simple as possible, but then you want to not make it so simple that it doesn't capture any interesting behavior. So our four forces, we're going to have, whoops, the weight of the mass is going to be, FW is going to be the weight of the mass. So M is the mass of the weight. Okay, and again, down is going to be positive, right? So that's why that's going to be a positive number. 2, the damping force. Damping. So the damping force is, or this is going to take the place of our air resistance, right? It's going to be working in the opposite direction of the weight, and so our damping, we'll call it F sub D. And I want my damping force to be proportional to velocity. Proportional to the velocity. And so therefore, let's see, I'm going to have my constant of proportionality equal to gamma, right? And then what's going to be the velocity? U prime of t. And then because it's acting in the opposite direction of mg, I'm going to make that a negative. Okay, so again, gamma is the constant of proportionality for the damping factor. Good. 3, restorative force. Okay, now to get the restorative force, we have to use another piece of information that we haven't discussed in class before, but you may have seen it in calculus or physics, and that is Hooke's law. And Hooke's law says that the restorative force is proportional to the distance the spring is from equilibrium. Restorative force is proportional to distance from equilibrium. Okay, so what does that mean? Right, that's proportionality. That's kind of a linear measure, right, of force. So the larger the distance from the spring, the more the force is being applied. Okay, we should say that this is only good for small distances, right? Because it is possible to mess up a spring, right? Have you guys ever done that? Stretch a spring beyond its ability to restore itself? So this is only good, really, for small u, and so that's one of our assumptions. Really only good for small, and I'll just put that in quotes, u. Okay, good. So let's, I think we need a mathematical statement for that. Let's see. Where is equilibrium for the spring? So the equilibrium for the spring is here, right? And so what that means, because the spring is not moving, the weight down, which is mg, is equal to the restorative force up. And what's that going to be? Well, by Hooke's law, that is proportional to the distance, and so that's going to be KL. And so mg, what we have then is equilibrium. Equilibrium implies that mg minus KL is equal to 0, right? And so then we also have, when the spring is in motion, then the force, we'll call it F sub S, is going to be proportional to the, well, it's going to be opposite in whichever direction it is. And then what's the distance to equilibrium? It's going to be L plus U of t, right? Capital L. Good. Okay, I think we have all of our pieces now. Can we put them all together? Oops, I don't have all of my pieces. I'm missing one. I'm missing number 4. Number 4 is external force. External forcing. And so, for example, you might have something on a piston, right? And then you might have your spring over here. And then this engine right here might be forcing the piston up and down, like in a periodic way, right? So your piston is shooting up and down, driving the spring. Okay, and so we'll call our external forcing F of t, capital F of t. Good. Okay, I think we're ready now for our model. And so the overall model is force is mass times acceleration, which in this case is mass times u double prime. And on the other side of the equation is the sum of our forces, F sub w plus F sub d plus F sub s plus our external forcing. Good. And so we'll just write down what everything is. Fw is mg minus gamma times u prime plus, minus k times L plus u plus F. Good. And so now, can we simplify this a little bit? Notice that here in red, we'll have mg minus kl, right? And then we'll have our other terms, minus gamma u prime minus k times u plus f of t. And why am I putting that in red? You might see it at the top of your screen. Okay, mg minus kl is equal to 0. So therefore those two terms will drop out. And now I'm ready to write my differential equation. Mu double prime plus gamma u prime plus k times u equals f of t. Good. This is the oscillator model. And let's talk about what these constants represent again. M is mass. Gamma is the constant of proportionality for damping. So for example, if you have no damping, gamma would be 0. And K is the constant, is the spring constant from Hooke's law. Good. All right. So we've got our model and we're ready to go. So, you know, I should make a quick side remark. The book likes to use pounds and feet because it's a very old book. So I've got a handout on our class website with spring models that are using metric units. So go ahead and do the homework from the handout on the class website. You can take a look at the book problems if you like, but because they're not in metric units, yeah, it's kind of a pain to work with. So we'll talk more about that in the next video where we'll just do some examples.